Hello everyone. In this video we will begin our discussion of carbon NMR. So we'll cover the basics, which identifying the number of signals and talking very briefly about the chemical shift, and then we'll conclude this video with a short demonstration on how we would apply this towards the characterization of a particular organic compound. So carbon NMR is particularly useful because obviously carbon is present in all organic molecules, and so there are numerous carbons in all the molecules that we talk about. And so having a direct way to measure those carbons and identify those different types of carbons could be particularly useful. In comparing this to proton NMR, the x-axis, so the chemical shift, is significantly wider. So again, typically the range for proton NMR is between 12 and 0 parts per million. So ultimately, it's going to be a much larger spectrum for carbon NMR. But the same idea of shielding and deshielding applies to carbon NMR as it does for proton NMR. So we can use carbon NMR to identify the unique number of carbons that exist within our compound. The one thing that's going to make carbon NMR a little bit simpler than proton NMR is that we don't have to deal with coupling or splitting. So typically we say that we work with decoupled spectra, so we don't necessarily have to identify the shape of the peak. So in some ways that again makes it easier for us to analyze the spectrum, but also in some ways provides less information about the connectivity of each individual carbon. Also, we don't have to deal with integration for carbon NMR. So ultimately, we're not going to be dealing with the area under the curve to tell us essentially how many carbons are present within that molecule. So here's an example of a carbon NMR spectrum. Again, you'll notice the longer or wider x-axis associated with this particular spectrum. And this is a carbon NMR of ethyl acetate. So notice that there are essentially 4 carbons in our ethyl acetate molecule. And so ultimately, we see 4 signals in our carbon NMR spectrum. So in this case, again, there's no symmetry in our molecule. And so each carbon is in its own unique chemical environment and therefore will appear in a different region of the carbon NMR spectrum. So we'll talk very briefly about the various different regions of the carbon NMR spectrum, but many of the same ideas of shielding and deshielding are going to apply to carbon NMR spectra as they are for proton NMR spectra. But before we do that, let's pause the video and just kind of quickly review the number of signals that you should see in a carbon NMR spectrum. Okay, so let's walk through these examples. So in this amine, we have essentially 2 signals because, again, thinking about the symmetry of the molecule, we have a plane of symmetry that goes directly down the nitrogen. So these 2 carbons are in the same chemical environment relative to the central amine as the 2 carbons indicated in blue. So you should see 2 signals in the carbon NMR spectrum. There are 3 signals in this carbon NMR spectrum of this ether here. Again, we have the 2 carbons that are on either side of the ether. And again, the connectivity of these 2 carbons indicated in blue is the same relative to the oxygen, relative to the functional group. So these 2 will appear the same. So there should be overall just 3 signals in the carbon NMR spectrum. We take a look at the cyclic ether, so this is THF, one of our polar aprotic solvents. Again, we have a plane of symmetry that goes directly down the oxygen. So again, we have 2 sets of chemically equivalent carbons, and so overall there will be 2 signals in the carbon NMR spectrum. So here is a very simple breakdown of the various different regions that we see in the carbon NMR spectrum. But again, they correspond very closely with what we see with a proton NMR spectrum. So notice that functional groups that contain pi bonds are typically more deshielded, so the numbers are higher in the spectrum. Again, that's due to anisotropy. The easiest one typically to notice is the carbonyl, so the carbon-oxygen double bond. That's going to be the most deshielded, so that will have the highest numbers. And again, that's typically between 220 and about 150 ppm. And notice also when we incorporate heteroatoms, so atoms not carbon, so nitrogen, oxygen, and sulfur. Again, the electronegativity of those atoms is pulling some electron density away from that adjacent carbon. So again, that's why we see a deshielding effect or a higher number for functional groups or carbons within those particular functional groups. And again, if we have sort of a saturated hydrocarbon, ultimately that's going to be the most shielded or the closest to zero. So oftentimes we don't necessarily just look at carbon NMR by itself. Typically what you'll do is do some sort of combined spectra problem. So you'll take carbon NMR in association with other characterization data, and that will help you to elucidate what the actual structure of your organic compound is. So with that in mind, you're provided the molecular formula, a copy of the carbon NMR and the proton NMR for an unknown. So go ahead and pause the video, and then we'll walk through how we would solve this particular problem. Okay, so probably the first thing to do here is to take the molecular formula and determine the HDI, so the hydrogen deficiency index. Again, this tells us the number of pi bonds and or rings that we have in our molecule. So if we were to solve for the HDI, we have an HDI of 1. So again, that tells me I have a pi bond somewhere in the molecule. Or a ring. So ultimately, we can pretty quickly identify that this is going to be a pi bond, that we're going to have a carbon-oxygen double bond, so a carbonyl here. Again, that's based on the chemical shift in the carbon NMR spectrum. So again, notice that we have a peak that's way downfield, so it has a large number. Again, that corresponds to a carbon-oxygen double bond, or the carbon that's attached to an oxygen as a double bond, so a carbonyl carbon. Also notice that there are 4 peaks, so notice based on our molecular formula, so each of the carbons is in its own unique chemical environment, so essentially there is no symmetry within the molecule. The rest of the carbons here are closer to 0, so fall kind of in that sort of saturated region. And again, that makes sense. We've utilized our pi bond, and the remaining atoms that we have are carbon and hydrogen. So again, that's about the most information that we're necessarily going to get out of our carbon NMR. So the location of the carbonyl we can't necessarily tell that directly from the carbon NMR, right? So I could have the carbonyl on the 1 carbon, the 2 carbon, or in this case, those are sort of my 2 possibilities. So if I take a look at my proton NMR, again, that can provide me additional information, and I can use that with the carbon NMR to solve for the unknown. So notice that we have 3 signals in our proton NMR, and again, 3 different regions with different integrations. So I have essentially, let's go ahead and identify the multiplicity. So we have a quartet as our sort of most de-shielded compound here. We have a singlet, and we have a triplet. So again, thinking about the corresponding partial structures to that, if I take a look at this peak here, so again, kind of working from the most shielded peak, again, we have an integration of 3, and it is a triplet, so ultimately we're going to have 3 hydrogens, and there's going to be 2 adjacent hydrogens. Again, n+1 rule gives us the multiplicity or the splitting pattern of a triplet, so that will be a CH3CH2. The singlet here we can generate based on our carbonyl. So what we're doing here is basically by putting the carbonyl adjacent to this, we have a splitting pattern that essentially sees no hydrogens, right? So again, based on our n+1 rule, it sees no adjacent hydrogens. And so a way to do this is thinking about putting that carbonyl sort of in the carbon chain, so we do not see any adjacent hydrogens. And also that corresponds to a methyl group on this side because it has an integration of 3. And then with that in mind, we basically have all of the carbon atoms that we need. And so ultimately, we need to take a look at the corresponding quartet. So ultimately, the quartet is going to be, I have this listed as the CH3, but it is actually the CH2 that corresponds to this particular compound, again, with an integration of 2. It's going to be the one that is closer to the carbonyl. So again, based on the chemical shift, that is going to be the one that is closer to the carbonyl. So again, ultimately, if we put all of those pieces together, we have our 4 carbons, and then we have our 3 other carbons that we did not necessarily assign from the carbon NMR spectrum, but based on the proton NMR spectrum, utilizing integration and multiplicity, we were able to identify the unknown compound.